All right, today we are diving into one of the most mind-bending discoveries in all of modern physics, time crystals. I want you to imagine, for a second, a piece of matter that just moves forever, seemingly breaking the most fundamental laws of nature that we all thought we knew.
So let's start with a really big question. What if matter could move forever without needing any energy at all? I know, it sounds exactly like a perpetual motion machine, right? The one thing science class taught us was absolutely impossible. But as you're about to see, the quantum world, it plays by a whole different set of rules, and it has some very, very surprising loopholes.
This whole wild idea really kicked off in 2012. It all started with a question from the Nobel laureate Frank Wilczek. He basically wondered, look, we know regular crystals break symmetry in space. So could there be a system that breaks symmetry in time? And that one question, that simple thought experiment, launched an entire new field of physics.
Okay, so to really wrap our heads around what a time crystal is, we first need to understand its more familiar cousin from the everyday world. We've got to build our foundation by comparing symmetry in space to symmetry in time. And we'll start with something we all recognize, a regular crystal.
Think about a diamond, or maybe even a single perfect snowflake. These are what we call regular crystals. And their number one defining feature is that their atoms are arranged in a super-ordered, repeating pattern in space. This perfect structure is what physicists call breaking spatial symmetry. Now, all that really means is that the crystal doesn't look the exact same from every single point. You've got this predictable pattern of atoms, then empty spaces, then atoms again.
And this right here, this slide just lays it all out perfectly. A regular crystal has a pattern that repeats in space. A time crystal has a pattern that repeats in, you guessed it, time. And that leads us to the most bizarre and crucial difference of all. For regular crystal, its lowest possible energy state, its ground state, is perfectly still, static. But for a time crystal, its lowest energy state is one of constant, rhythmic movement, an oscillation that just keeps going and going, forever.
But wait a second, perpetual motion? That should be setting off all sorts of alarm bells. It seems like it completely violates the laws of thermodynamics. So let's get into the clever twist in this story, the quantum loophole that actually makes all of this possible.
So the first major roadblock was a big one. Physicists pretty quickly came up with these mathematical proofs. They're called no-go theorems. And they basically showed that a time crystal just couldn't exist in a state of thermal equilibrium. For a minute there, it really looked like the whole idea was dead in the water.
So what exactly is this equilibrium state? Well, it's just a state of perfect balance, of rest. It's where energy has all evened out. The best example is a hot cup of coffee you leave on the counter. It doesn't stay hot forever, right? It cools down until it's the same temperature as the room. It settles. And that natural tendency to settle down and stop is exactly why perpetual motion is forbidden. Systems just naturally lose energy and come to a halt.
And this is where the genius breakthrough happened. Scientists realized, okay, we can't make a time crystal in a system that's just sitting there, left alone to rest. But what if you don't leave it alone? What if you use a system that's constantly being pushed from the outside, what they call a driven non-equilibrium system? This was the loophole. The time crystal isn't actually violating physics. It's just cleverly existing in a state where it's always being nudged along.
So, the theory was patched up. It was refined. But the big question remained. Could anybody actually build one? So let's turn from theory to the lab and see how scientists brought this totally bizarre idea to life.
And then, in 2017, it happened. A team at the University of Maryland, led by Christopher Monroe, basically followed this recipe. First, they took a chain of ions, ytterbium ions to be exact, and just held them in place with electromagnetic fields. Second, they gave the system that push we were talking about by zapping it with perfectly timed laser pulses. And third, they watched and they saw something absolutely extraordinary.
The ions didn't just flip back and forth in perfect time with the laser. Nope. Instead, they started responding at exactly half the frequency of the laser pulses. This is what's called a subharmonic response, and it was the smoking gun. It proved the system wasn't just a puppet mirroring the laser. It had adopted its own stable, unique rhythm. It was ticking like a tiny quantum clock, but at a different rate than the clock pushing it. This was it, the world's first discrete time crystal.
And just look at the incredible speed of progress here. The idea was just a theory on a blackboard in 2012. By 2017, the first ones were actually made in labs at both the University of Maryland and Harvard. Just a few years after that, in 2021, they scaled the whole experiment up on Google's Sycamore quantum processor, proving this wasn't just some one-off fluke. The pace of discovery has been, well, absolutely staggering.
So we have this bizarre quantum phenomenon that ticks forever without using energy. It's fascinating for sure, but you might be asking, so what? What's the payoff? Let's talk about why this actually matters in the real world. The potential applications here are nothing short of revolutionary. Because time crystals are naturally so stable and so resistant to being disturbed, they could solve one of the single biggest problems in quantum computing, creating stable quantum memory. And beyond that, their unique properties could lead to hypersensitive sensors and new tools for making ridiculously precise measurements of time itself.
So here's the crucial takeaway. This is the big one. Time crystals are not just some lab curiosity. You know, we're all taught about the phases of matter: solid, liquid, gas, plasma. Well, time crystals represent a fundamentally new phase of matter, a phase that finds its pattern not in space, but in time. We've literally had to expand our definition of what matter can even be. And that, of course, brings us to a final thought. The discovery of time crystals forced us to rewrite the textbooks on our definition of matter. It proved that an idea that seemed totally impossible was actually just a hidden rule of the quantum world. So it makes you wonder, what else are we wrong about? What other fundamental impossibilities are just out there, waiting to be discovered?